Okay, this is try number two. Because of the wonderful policies of IT, they decided to suddenly uh, restart my computer while I was in the middle of recording. Thanks, guys. Um, okay, so where were we here? We're talking about power and how it's related to the torque. And so I guess like one thing that I was a little bit surprised of is that I didn't really find like a clear, easy explanation in any of the introductory textbooks. So I thought that I'd give my own way of understanding this. I mean, of course, you can just sort of take it for face value. Okay, power is torque times omega, but I maybe help you in a couple of different ways to think about this. So in a linear case, work is force times delta x, right? So if your force remained constant, you would say, oh, my delta work would be force times delta x. I would integrate up to some position, so 0 to some distance L, and my work would be the force times the distance. Maybe all of you are familiar with this result. But power is work per time, right? And if the force is constant and we have distance per time constant, then that means that power is force times velocity, right? It's maybe not something that you use every day, so I thought maybe I just remind you. So this is very similar to that um, power is related to torque um, and times omega. But I guess the way that I can think about this here is that if we have a circle and we have something that's moving around on a circle here like this, if we have a theta and we have an r, then this arc length that this object might move, say we're pushing some weight over from here to here, that distance is going to be r times theta, right? So I guess maybe one way to think about this then is maybe we could say that the amount of work that we do, torque is going to be the force at some distance away from the rotational point. Um, and we could say that, you know what, r times theta, right? R times theta really is this s. So that's my force times the distance, basically, right? So that's why I'm saying that this is like force times the distance. This is kind of like, I mean, it is a distance, right? But this is like, I'm just making an analogy here to like, this is my force times the distance here. So again, if I were to take the time derivative of this, right? So I'm going to take a d by dt of all this here. That's going to be power, in other words, work per time or energy per time. And imagine that this force is constant, the radius is constant. So the only thing that's left is this theta, right? So theta dot, so the force times this distance here, that's my torque, times theta dot, which is going to be omega. So this here is my torque, and this is omega. And hopefully I've helped to demystify why the power is torque times omega. So that's something there that I hadn't realized that needed to be more clarified. Um, and so in this problem with the generator, we were asked to sort of think about the power both from a electrical perspective, right? So the amount of power that's dissipated into a resistor, but also to be thinking about the amount of torque that we would be doing, right? And so imagine that if you have this sort of wire here, you're going to have a magnetic force both on this and this as it's rotating through the magnetic field. So see my solutions for a little bit more clear detail. I just wanted to put sort of kind of some words on the air so that at least it makes a little bit of sense, and then you can dig in for more detail in the solutions. So lastly, I'll just talk about what's called as the root mean squared. So this is an idea that if you have a voltage that's oscillating like this, so V is a function of time, and you might be asked something like, oh, hey, what's the average voltage? Well, it's sort of an ill-defined question because the average voltage is 0 in this case, right? It doesn't really make sense to talk about the average voltage. So instead, some smart people came up with this idea of like, well, hey, what if I were to square this so it looks like this? It ends up being kind of double the frequency, right? Because every time it crosses 0, it's going back up again. So this one here is corresponding to this one here, and so on. And then let's take the average value of that, and then let's square root it back again. So this is called the root mean squared. In fact, it's kind of done in the opposite direction, right? You take the square, then you take the mean, and then you take the root of that. So that's the root mean squared. Another thing that maybe is worth talking about is that if you solve for this for the instantaneous power, going back to this idea of the power is equal to this e squared over r, you got something that was proportional to a cosine term. So I'll write this here: omega squared over r cosine squared of omega t. And if you wanted to find the average power, you're going to need to find the average of the cosine squared function. So cosine is a function or cosine squared is a function that's going to look like this. And it turns out that if you took the average of this, you took the average of this going between 1 to 0, maybe you can intuitively see that it's supposed to be at 1/2. But you can also do the cosine squared of omega t averaged, time average, would be like taking from some minus t to t of cosine squared of omega t dt. And if you integrate this, say over a complete cycle, you'll actually find that this is equal to 1/2. This is a very common result in a lot of physics problems, so I thought I'd mention it. You can intuitively understand it if you just say, oh yeah, here's something that's going between 0 and 1. Looks like half the time it's in between. But if you wanted to be sure, you could perform this integral, and the way forward to doing that is by using trigonometric identities. Don't try to integrate it as it is, unless you want to use maybe Wolfram alpha. Okay, good. So that is our discussion of homework 9. Let's find our sheet here. So I reviewed some points. Let's take a look now at Ampere's law revisited. So energy in capacitors and inductors. I did not do that yet. So okay. So here's just something that I thought was interesting when I was sort of thinking through this again. Earlier we looked at a capacitor plates, pair of capacitor plates, and say that this one has a bunch of positive charges on this one has a bunch of negative charges, then there's going to be an electric field, right, in between these plates. We saw that the energy that's stored in a capacitor is either 1/2 C times delta V squared, or it's 1/2 Q squared over, or Q squared over 2C, right? That's another way of looking at it. But actually, and then we had this idea that the amount of energy per volume, so the energy per volume was equal to this E squared with an epsilon naught over 2, okay? And this was meant to be sort of an analogy with the B squared term that we saw for a solenoid. And I wanted to sort of make a simple proof, and it ended up not feeling so simple in the moment, but I wanted to show you that maybe it is simpler than we might have thought. And so my simple way of going about that is that if this is our expression here, we can see that the electric field in between two capacitor plates is actually going to be sigma over epsilon naught, which is also Q over A epsilon naught. And this result is actually going to be very useful in just a moment, believe it or not, when we start talking about Ampere's law. So this is the electric field between the two plates. I'm being a little sloppy right now with the direction. You all know that it's in the downward direction. We use it when we need that. So we can also say that the voltage, right, is sort of ramping from higher to lower in a linear fashion. And so in that sense, we can say the electric field is the slope of the voltage, right? So in other words, electric field is delta V divided by distance. Maybe this is the distance between the plates here. And, or in other words, the delta V is equal to E times the distance between the plates, right? It's a uniform field, so we can do that. So if I wanted to, and I could also see that for a capacitor, the capacitance is epsilon naught A over D. So if I wanted to, I could actually replace this as epsilon naught A over D for the capacitance. And for the voltage, I could rewrite this as ED, where I'm changing this as Q over A epsilon naught, and then this is my D here, so you believe me that this is my expression for voltage, and I can rewrite this as then QD over A epsilon naught, and it's going to be squared, so I'm going to rewrite it twice, QD over A epsilon naught. And so it looks like one epsilon naught cancels here, one of the D's cancels here, and one of the A's cancels with this one here. Does that look good? Yes. Oh, you know what? I'm sorry, I just realized that I'd like to do it a slightly different way here. I would like to replace the capacitance with epsilon naught A over D, but I'd like to leave the expression for the electric field at the moment as just this E times D. So this is going to be E squared times D squared. Okay, you'll see where I'm going with this in just a moment here. So that means that this D cancels out with one of these D's, and I'm left with 1/2 epsilon naught A times D times E squared. And this is the energy. But this right here is the area times the distance. So this is the volume of this sort of rectangle, or I mean of this what do you call it? It's not a cube, but it's a, you know, cubical thing. So I can rewrite this as U per volume is equal to 1/2 epsilon naught E squared. And this was the sort of kind of sketch or derivation that I was hoping to get at very simply, but of course one needs to make the right assumptions in order to do so. Okay, good. So this helps to justify this idea here. And of course, just to review, we also had taken a look at this idea that the energy that's stored in a solenoid, right, or something that has a self-inductance was 1/2 Li squared. And there's a connection there to saying that the U per volume is equal to B squared over 2 mu naught. And so you can see that there's this sort of beautiful connection between this E squared term and this B squared term, right? The one has a epsilon naught on the top, one has an epsilon naught on the bottom, but there's a symmetry that's going on between the two. Okay, moving on, let's talk about Ampere's law. So everybody knows that for a wire that has a current that's going through it, if I made an Amperian loop that was centered on this wire here, some radius r, something like this, then I can say that B dot dl is equal to mu naught times I enclosed. What do I mean by I enclosed? Well, I mean I that pierces through this loop here. So far, so good. Well, all right, it's so far so good, but what if this current went to a capacitor plate and was starting to charge up the capacitor, right? There's nothing in the rules that's like against this idea that like my Amperian loop does not necessarily have to be like a soap film that goes exactly on this thing here. It could be a soap film where I blew into it and made it a little bit of a other shape like this, right? Or it could be a shape that's like this, right? And if that's the case, there's something weird going on. There's an area here where there are no charges that are crossing through. So the I enclosed seems to be 0. So is it 0 suddenly if I change my surface around my Amperian loop? That seems a little bit strange, right? That's like, so this is, remember that this I enclosed is like a J dot dA around the surface that is bound by my loop, by my Amperian loop. And this is still a surface that's bound by my Amperian loop. So what is going on? Well, this is the sort of breakthrough that Maxwell made, is that he thought, all right, well, okay, so maybe it's true that there's no current going through here, but there is at least an electric field going through here, right? we're starting to supply positive charges here, and we're getting negative charges over here. And the electric field, as we were just mentioning a moment ago, is this sigma over epsilon naught, or it's Q over A epsilon naught, right? And so I wonder if we could work with that here and say, well, I have a, you know, I have, instead of a current enclosed, I've got this electric field kind of like a flux, basically, right? So I wonder if we could think about it in a slightly different way. For example, what if we thought of it in terms of that there's a flux, so there's a flux, efflux, going through this surface here that's equal to the electric field times the area. I can get away with this again in this case because the electric field is technically E dot dA integrated, right, over this two-dimensional area, but over a capacitor plate, that's, it's a constant electric field, so we can multiply it by the area, right? So rewriting this here, this could be Q over A epsilon naught, just filling in for this value here, and times my area. Oh, interestingly, the areas cancel out. So I wonder if I could sort of massage it so that this flux term could sort of make up for the fact that I didn't get my I enclosed. Well, if we look at the derivative of this here, we can see that that's going to be equal to Q dot over epsilon naught. But wait a second, Q dot, that's just dQ by dt, right? That's the same thing as the current, right, that was going into the wire in the first place, right? So here's my current going into the wire in the first place. So I wonder if we could sort of re-massage this here so that if we had a term that was this phi E dot, or d phi by dt, right, to be more formal, and if we multiplied that by an epsilon naught, then we would get that I term, right? Well, and then there's also this mu naught term, so maybe we should put that in there too. So what we did is we just derived the last term on Maxwell's equation. So we can add this now, so to mu naught times I enclosed, and set it equal to B dot dl. And now we have a foolproof plan, because even if we chose our surface that it goes around here instead of over here, well, then we won't get the I enclosed, but we will get this term that's going to give us the same thing as that. So then dilemma solved. Now, we weren't just solving a simple little puzzle here by doing this. We were actually fixing the broken part on Maxwell's equations. And so to show it in the differential format, it looks like this. Mu naught times J, and we have plus mu naught epsilon naught times dE by dt. And we can get this by realizing that this is just a double integral, this is just a double integral, and this we can change back to a double integral if we go the other way with the Stokes law. So that's the differential format. And this has profound and meaningful consequences for Maxwell's equations. And I wanted to show you. I had it open earlier, but let me go ahead and open up my canvas here so I can show you. It should, here it is, okay. So in Canvas, I attached a short video that talks about Maxwell's equations and actually kind of like gets at this idea here. So if you go to Maxwell's equations, you can download a short video here. It kind of has like a History Channel sort of vibe.
Faraday sought the seat of the phenomena.
And they help you to,
Magnetic circulation.
I'm trying to find
What is the magnetic circulation equal to?
so here's the dilemma that they're referring to here, is that this wire is coming in, there's these capacitor plates, and they made this bubble between the two plates. And it's sort of giving you a historical dramatization of the discovery of this, or sort of thinking through it in a different way. I think it's a good video. It's a little outdated. It's kind of it's got that 90s vibe to it. But anyway, it explains to us that there is another source of this Maxwell's term. So now we've completed Maxwell's equations, which is really cool actually, and it's going to have some really profound consequence, which I'm going to give some hint to right now. So, oh, and by the way, also that one of the things that was stimulating this inquiry was this idea of thinking about waves of electric field. And if you watch the short video from the Maxwell's equations, you'll see that there is that people were after this because they knew that in space there wasn't any matter. And so if there was matter, if they knew that if there was, and we'll get into this a little bit more together, but but they knew that if there was waves of electric field, then there should be a circulation in electric field, which meant that there was a time varying magnetic field according to this equation, right? And so therefore there should be a magnetic field. But if there wasn't this term here, if there's a magnetic field and there's a curl of a magnetic field, then there should be a J. But in space, there's no stuff. So there can't be any J, and so therefore there can't be any magnetic fields, and then there can't be any waves of electric field, right? It's a lot to digest, but those are the steps. And we're going to go over it a few different ways so that you can see how it's working. But I just wanted to share with you something that I think is so cool and interesting, which is that we have all of our equations now for Maxwell's equations, right? We have this one, we have this one, we have this one, and now we have this one. So if you're looking for any cool tattoo ideas, this just might be it. I mean, make sure to, put vectors over the proper things, if you're gonna, I mean, I guess you can always put a vector over things later if you want to touch up your tattoo. But I wanted to show you something that's really cool, and it's gonna be a little sloppy, but we're gonna do it so that we can sort of see the origin of electromagnetic waves, and this will give us sort of a hint. If you look at these equations here as like, this is like a d by dx of electric field is equal to minus d by dt of magnetic field, and that this is like a d by dx of magnetic field is equal to, in space there's no j because there's no stuff, but I can rewrite this as then mu naught epsilon naught times d by dt of E. Now, a cool thing that I can do at this point is I could say, well, what if I were to take a d by dt of this whole equation right here? You can always flip differential operators. So I could rewrite this as d by dx of d by dt let me do it a slightly different way. I want to do d by dx here. So d by dx of d by dx of E equal to minus d by dx of d by dt of B. But I can flip these here, so I'll do d by dt of d by dx of B, and I can fill in for this one here. So this ends up being then second derivative of E is equal to minus d by dt of this stuff, which is this stuff I've just underlined here. So then this is going to be mu naught epsilon naught d by dt of E. So what we have here is a second derivative of E is equal to minus mu naught epsilon naught times the second derivative of electric field. This equation right here is called the wave equation. And if we work through it a little bit more, we actually find that the speed of light is related to this 1 over mu naught epsilon naught with a square root. This is going to be the speed of light, and we'll get to that a little bit more later. But I wanted to just show you that right off the bat, we can actually see that the wave equation is coming right out of this modified Maxwell's equation. So we made a huge amount of progress. It didn't take that much math, but it took some logical arguments. And I just wanted to last show you a Python notebook that gives you a way of making some sense. I'm going to put this up right after I upload the recording to show you some ways that you can play around with the amplitude and you can play around with the phase. There's these so-called sliders. You can change the frequency. I think most importantly is not just like playing with it and saying, oh, wow, it works, but looking at the equation that I've written down here, writing down the equation yourself, seeing if you can make sense of what's happening in terms of the expressions. There's a few things for you to try in here. It's not really like a formal homework assignment, but I thought that it might be helpful. If you see something like this, you can actually begin to understand how these waves are actually working. So that's something that I put on, and I also put it in exponential format, this complex exponential, because I thought that might be helpful. So please check that out. That'll be under the supplemental materials. I believe what I'll do is, let's see here, where would I put this? Put it in, I'm going to make a separate section called Python, so that we have this. Actually, we'll put it into tutorials actually. So I'll put it in there as a tutorial. Okay, good. And then we're from here. So we want to be talking. We're starting to move. I think that when we meet back up after the break, let's go through the complex impedances. If you wanted to look over it a little bit, you can take a look at the worksheet that's posted here about the complex impedance, tutorial number 15. Let's go through that together. We'll sort of finalize a discussion of that. And then we're going to start moving into talking about electromagnetic waves. And it's a really cool topic. Obviously, it's like, it's like a huge topic for anywhere from X-rays, radio waves, you name it, visible light. I mean, almost everybody's research in the whole world has something to do with electromagnetic waves on one level or another. So, and it's actually such an important part of our lives. Without that, we wouldn't, have these little devices, right? These are all built upon electromagnetic waves. So we'll be talking about that. We'll be talking about some applications. We'll be talking about how light interacts with matter, just a little bit, kind of scratching the surface and getting a sense for how dipoles oscillate. Anyway, it's going to be really exciting. I'm trying to prioritize information, as best we can so that we get the most out of this course. There are a few things I'm skipping over. I wanted to mention that we are skipping chapter 8. So chapter 8 is about conservation of energy, and it does involve a lot of vector calculus. And yes, it's important in the sense that, like, if we were trying to prove or understand where energy goes, we'd need to understand this content. But I still think that we can get a lot out of this class without going through chapter 8 materials. So I just wanted to alert you of that. We're moving into chapter 9, where we're really talking about electromagnetic radiation. Okay, so I'm trying my best to find that balance between being too math heavy, but also still getting the right balance. So if you have some feedback from me on that, or there's some topics that you'd like to see covered here from chapter 9, let me know and I'll try to work it in. So thanks everybody, and hope you have a good break.